Okay, so last week we looked at the renormalization group flows, and we discussed the general properties of renormalization group flows, and we looked at particular examples of the 2D Ising model and the next nearest neighbor Ising model and the nearest neighbor Ising model, and we looked at specifically what a snapshot of the flow diagram looks like. Looking at the critical manifold and then looking at the flows off that. And we understood how universality emerges due to the fact that the repulsive directions are the eigendirections at the critical fixed point, and that the phases of the system correspond to the sinks of the renormalization group flows. So at the end of last time, what we did was then we saw how we can construct the phase diagram by looking at the ways that the coupling constants flow as you go towards the sinks, and from that we can then deduce the phases of the system. And then lastly, we looked at how one can relate the renormalization group eigenvalues to the observed thermodynamic and correlation critical exponents. And I just gave a very simple example of a sort of one-dimensional renormalization group transformation, showing you how one can then deduce the critical exponent nu, and following kind of like what we did with the Kazanov block spins, except with the difference here that we actually know how to calculate the exponents because they are actually eigenvalues of a linearized renormalization group transformation. So what we're going to do today is we are going to do renormalization group for the 2D Ising model. We're going to do a particular instantiation of it called the real space renormalization group, not the field theoretic momentum space version that some of you may have heard about. And then we're going to show how we can go backwards and start with the Onsager's exact solution and then deduce what the renormalization group eigenvalues should be exactly. So that's what we're going to do today. I've started Zoom and I've started recording. If anybody, by the way, I put the Zoom link on Teams, just in case anybody has to miss a lecture. Can somebody just check that we're recording okay? I think it was you did it last time. Before we get on to doing the RG, I want to just finish one topic that we didn't quite finish last time, which was the differential renormalization group. So the idea in the differential renormalization group is simply that we can write the renormalization group recursion relations in differential form, where we take the idea that we do a renormalization group transformation, but now we make it an infinitesimal transformation. And that way, instead of it making it a block like 2 or 3 or 4, lattice spacings, we now make it 1 plus epsilon and go to the limit and make a differential RG. So the basic idea is we start with a lattice with spacing A, where we do a renormalization group transformation to block size of L times A, and then we construct blocks of size S times LA, where S is some number between 1 and infinity, and then eventually we let S become 1 plus epsilon. So here's what you get if you do that. So at the bottom of the page, at the right, what I'm showing you here is the renormalization group transformation after I've done a transformation by L and then now make a transformation by a factor of S. Then what I simply do, no, thank you. Then what I do is I simply subtract the image of the coupling constants at 1 plus epsilon times L minus the original ones at size L divided by L epsilon, and that gives me the differential form. And that differential form, I can write that as the derivative of the renormalization group transformation with respect to S, setting S equal to L, and that quantity we will call 1 over L times a function B of KL, which in other contexts becomes known as the beta function. And so what we see then is we have a differential equation in log L because I've got this factor of L, so I've got dr by ds 1 over L, so that gives you k by d tau is this function b of the coupling constants, and so this is just a differential equation. It's a set of nonlinear differential equations for the coupling constants, which has to be solved in order to find the behavior of the system as you normalize. And what happens, of course, is that we're interested in the fixed points. So the fixed points are when the b function is equal to 0, and then we can linearize around that fixed point, and from that deduce the relevant and irrelevant variables and so on. So this is just the form that if you look at papers that use renormalization group, particularly those during the 1980s, when renormalization group was just still being developed, this was a very popular way to formulate the renormalization group. So you would just simply take the variables, construct these renormalization group differential equations, and then you would just solve these nonlinear simultaneous differential equations and find the behavior of the system. But conceptually, it's exactly the same as what we've done before. Okay, so now so why is this useful? Well, the whole point of this is to be able to start where as you course grain, of course, the correlation length is getting smaller and smaller. And so eventually it gets to be so small that actually none of the complications of the critical region become apparent. The correlation length is now, as you normalize, the correlation length gets smaller, so you move further and further away from TC. The further away you go from TC, then it's possible to use mean field theory, it's possible to use perturbation theory, so you can match the renormalization group flows onto the results that you get from doing regular perturbation theory. And so this is a very useful way to do things. Okay, so that being said, let me now change gears, and we're going to do section 9.6. So we're going to do the renormalization group for the two-dimensional Ising model. And what we're going to do is actually a real space renormalization group. So let me show you exactly what I want to do. So I'm going to do this. I'm going to take a picture here. I should have done this before, but I didn't. All right, so let's put this into our notebook. Like so. There we go. All right. So what is our goal in this section? So our goal is to present a simple real space RG transformation. And we're going to do this on a triangular lattice. And the reason is that on the triangular lattice, it's very easy to define blocks that have a specific size. So for example, over here, this here represents a block spin. So we're going to take triangles of spins like this. And then once we've done that, then what we're going to do is then build and the next block is going to be taking these block spins and then putting them together, and so on and so forth. And it's very easy for us to construct these block spins in the way that I'm showing you in this picture. So refer to this picture if you want a guideline for what it is that we're actually doing. Okay, so let's get started. So the starting Hamiltonian that we're going to use is our usual one. So we're going to say that it's K, which is J over KT, the sum over nearest neighbors, SI Sj, and then an external field H, and then sum over I Si. So that's our starting picture. And then what we're going to take as our block spins is what I drew on the previous page. So I'm going to say, let's take the block spin Si to be the sign of spin 1 in block spin I plus spin 2 in block spin I plus spin 3 in block spin I, like so. So each block, what we're imagining is I've got my block like that. And so it might be something like this. This would be S1 block spin I, S2 block spin I, S3 in block spin I. So that's the renormalization group transformation that I want to do. And so once we take these spins and then build a block spin out of those. So what is the size of the block spin? So the lattice of the block spins, which is the blue thing on the previous page, that's enlarged from the microscopic lattice by a factor. L is the square root of 3. And you can just simply see that just by doing some very simple geometry. So now we know what the block spin lattice is. We also know that our spins Si, because they are defined as this majority rule transformation that we've been using, then that means that they have the values plus or minus 1. So what we're going to do now is we're going to construct our normalization group transformation explicitly. So I'm literally going to compute it. And then we're going to compare with Onsager. And what Onsager did in 2D, and in the case where the external magnetic field is equal to 0, what he showed was that alpha is equal to 0, and the critical exponent delta that tells you about the breakdown of linear response theory, that has the value 15, and then there's various other critical exponents that I listed for you on a previous in a previous lecture. So what our strategy is going to be is we're going to do the following. So step 1, we're going to use Onsager's formula to calculate what should be the exact renormalization group eigenvalues. So we're not going to compute the critical exponents themselves. What we're going to do is meet in the middle. So we have Rg on one side, and we have the exact solution on the other. The renormalization group will grind away, and we'll eventually be able to get the critical exponents, but we can meet in the middle. We can calculate from the renormalization group what are the renormalization group eigenvalues. We can go backwards from Onsager's solution and calculate what the Rg eigenvalues should be, and that way we can easily compare them. And that's what we're going to do. So we're going to use Onsager for that, and then what we're going to do is that's going to be step 1, and then step 2 is calculate the eigenvalues approximately using a real space renormalization group. Okay, so that's the idea. So let's do the easy part first. So step one, I'm going to calculate Onzaga's formulae. So what do I know? I know what alpha is. So I'm going to use the Josephson scaling law that I derived at the end of last lecture. 2 minus alpha is nu d. So we know that d is equal to 2, and we know that alpha is equal to 0. And so that tells us that nu is equal to 1. And if nu is equal to 1, that means that the renormalization group eigenvalue y sub t is equal to 1. Okay, remember that nu was 1 over y sub t. Then the actual renormalization group eigenvalue is lambda t, that is L to the power y sub t, and L is equal to root 3. So that is equal to L, and that is equal to root 3. So if I do a renormalization group transformation, do the linearization, calculate the eigenvalues, one of those eigenvalues, lambda t, has to have the value the square root of 3. Okay, now we know that there's two relevant variables. In order to get to a critical point, we have to adjust the temperature to the Tc, and we have to adjust the external magnetic field to 0. So now we're going to compute the other renormalization group eigenvalue. So let's go ahead and do that. So for lambda h, how do we do that? Well, remember that there was a scaling law that we derived in a previous lecture, when we derived the correlation length scaling. So that was going as d minus 2 plus eta, and so we have that. Now, what Onzaga showed is that eta is actually, I'll put this over here, eta is actually 1/4. So that's the exact result for eta. And so that means that y sub h is equal to d plus 2 minus eta over 2, and then that is equal to 15 over 8. So that's from this scaling law, putting in d is equal to 2. And then the critical exponent, well, not the critical exponent, the renormalization group eigenvalue is then L to the power y sub h, but L is the square root of 3. So this is the square root of 3 to the power 15 over 8. And when you calculate that, you get a number that's about 2.80 ... So that is the result. That if all of this works, when we do the renormalization group, we should get a value that's the value that we would expect to get. So notice that lambda h and lambda t, these are the two renormalization group eigenvalues, those do depend on L. Okay. But the critical exponents do not depend on L. Okay, so now let's go ahead and do step 2. And in step 2, what we're going to do is literally construct the block spins. So we have our picture that's over there on the left. So I'm going to use a notation. So I'm going to denote the microscopic spins within a block named I. I'm going to denote those, just to save writing them, I'm going to call them sigma I. So when I write down sigma I, what I mean is the vector S1I, S2I, S3I. Okay, so and the block spin variable is S capital I. So that's the notation I'm going to use. Why am I going to use this notation? Well, because later on, if we have time to do this, I'm going to just show you a little bit about a momentum space for a normalization group. But the exact same procedure that we're doing here, where we're getting rid of the microscopic degrees of freedom, what our goal is going to be is to sum over sigma I. All of those degrees of freedom, we're going to get rid of those and just retain the long wavelength degrees of freedom. So that's what we're going to try to do. So the way that we're going to do the coarse graining the way we're going to do it is I'm going to enumerate all the possible microscopic states of the system. That are consistent with a given macroscopic state of the system. So let's take, for example, the state Si is +1. Okay, so let's enumerate all the possible vectors that we could have for sigma. So let's list those. So I could have, for example, one of the spins pointing down and two of them pointing up, like that. That would give you, since we're doing the majority rule, more spins are pointing up than down. So that would be a configuration. And then another one, all I've got to do is really enumerate these so I can move that down spin to any one of these three positions, like so. And then there's another spin configuration where all the spins are pointing up like that. And so those are all the microscopic states of the system consistent with S is +1. All right, let's now do the same thing for S is equal to -1. And you can guess how that's going to work. So it's just going to be the exact time reverse opposite of those. So those are all the configurations. If you give me a block spin value, those are the microscopic configurations that are consistent with that. So let's just do a quick check to make sure that we have not lost any degrees of freedom. Do we have the right number? Of degrees of freedom. So let's start off with our microscopic lattice. So microscopically, we would say, well, I've got this this block. I've got three spins, and each of those can be in two states. And so that gives me 2 cubed is equal to 8 configurations. So that's what you would say if you were looking at the microscopic states of the system. If you looked, on the other hand, at the macroscopic states of the system, what would you say there? Well, you'd say, well, I've got two block spins. That's SI is plus or minus 1. So I've got two of those. And then for each of those, there are 4 corresponding microscopic configurations. And so therefore I've got 2 times 4 is equal to 8 configurations. So what is my conclusion from this little calculation? So what we conclude is that these descriptions are equivalent. And that really goes back to the thing that we discovered a couple of weeks ago, that if you look at the partition function doesn't change under a renormalization group transformation, because what you're doing with renormalization group is you're just summing over the degrees of freedom in different orders and in different combinations. But you still end up with the same number of states that you have to sum. Okay. So that's the counting. Now, what is the thing that we want to calculate? So the next thing we want to do is we want to say, what do we want to calculate? And so what we want to calculate is the effective Hamiltonian. So how do we calculate the effective Hamiltonian? Well, remember how we defined it. We defined it like this. We start off over here on the right with our original Hamiltonian, the Ising Hamiltonian. But now I'm going to write every state of the original Hamiltonian in terms of the block spin variables, SI, and the microscopic variables, which I've called sigma. Okay, so those are 2 equivalent configurations. And now what we're going to say is, well, what I'm going to do is I'm going to sum over all possible sigmas, the microscopic configurations, consistent with a given SI. And so what I want over here on the right-hand side is I want to have the effective Hamiltonian, which I'll call H prime, and that's only going to depend upon the block spin variables. And so in order to get that, what I have to do is I then have to do a trace over the microscopic configurations sigma I. So I'm going to make a trace over the microscopic configuration sigma I of my original Hamiltonian. In renormalization group language, we say that we are integrating out microscopic degrees of freedom. In this case, it's the sigmas. And then at the end of the day, after we've done that, the effective Hamiltonian, just depends on the block spin variables. Like so. Okay, so that's what we have to do. So when you see any paper, like when you're reading for your term essays or in your research, you see any papers on the normalization group, they're going to be full of complicated calculations, Feynman diagram calculations, all sorts of weird and wonderful things like that. Whenever you see that, just ignore it, okay? It may seem very complicated, but all you're doing is all of the complexity of the calculations is doing this partial sum here. That's where it all becomes complex. So the only thing that matters is that after you've done the effective Hamiltonian, after you've constructed that, then we can read off the RG recursion relations for the coupling constants. So in other words, once I've constructed the effective Hamiltonian H prime, I can then look at that and say, well, it's got some nearest neighbor terms, some next nearest neighbor, some next nearest neighbor, some triplet interactions, quartic interactions, blah, 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 everything you want. And so I can then read off how those coupling constants are transforming, and that's how I construct my renormalization group flow. And we're going to see for this example, the renormalization group transformation turns out to be quite simple, and so we can easily read those things out. So that's the roadmap. So now let's try to do that. So the way we're going to do this is a kind of perturbation theory. And that type of perturbation theory is actually a cumulant expansion. Well, if you don't know what that is, I will explain it in a minute. And this corresponds to computing a certain set of Feynman diagrams. For those of you who know quantum field theory, this would be connected Feynman diagrams, and that's what we're going to be doing. But it's going to be much simpler. So let me just make a note here, so that when we talk about usually in perturbation theory, when we say perturbation theory, what it means is that you expand e to the x. So if you've got a Boltzmann factor, or you've got an action in a quantum mechanics problem, that you've got a factor, a Boltzmann factor like e to the something, e to the x, then usual perturbation theory is just expanding e to the x as a power series. But we're not going to be doing that. We're going to be doing a cumulant expansion of e to the x. And I'll show you what that is. Okay, and then the first thing is we're going to do first of all the case where there's no external magnetic field, and then later I will show you the results with external magnetic field using a dirty trick. Okay, so here is the basic idea. What we're going to do is we're going to take our Hamiltonian and we're going to write it as the interactions within a block plus the interactions between blocks. So that's our idea. So we're going to write it in this term, and then in this term, and then what we're going to be able to do is calculate the integrating out the interactions within a block. So then we're just left with the effective interactions between blocks. So when I write it like this, what I'm going to say is that H is equal to, well, I'll call this as H naught, and then this I will call V. So let's go and then read off what H and V are. And we can easily do that because we know over here, here is our picture of our blocks. So all I have to do is write down the sum between the spins S1i, S2i, S3i in the block, and then interactions between spins in different blocks, which are shown in this picture over here on the left with the blue lines. So that's how we can write it down. So let me go ahead and just do that for you. So H naught is just the sum over every single block I, and then I sum over spins I and j within the block I, and then I have the coupling constant k, and then si sj. So that's the Hamiltonian for the interactions within a block. Then for the interactions between blocks, so that is just k, then the sum from block I and block j, which are not the same, and then I'm going to sum over all the spins in I, all the spins in j, and then si sj, like that. So that's that's our picture. And so let me literally draw this as a picture. So here are block spin I and j, like so. Let me draw the variables. So here would be 1, 2, 3, and then 1, 3, 2, like so. And then we know that the spins interact with their neighbors, and so we can see that there's terms where this spin over here is going to interact with its neighbor within the block, but then this spin over here interacts with its neighbor. That's an interaction in V, and this is an interaction within H naught. Okay, so that's our picture. So what we're going to think of then is that H naught is our unperturbed Hamiltonian. And V is our perturbed Hamiltonian. V is our perturbation. So what we want to calculate is over here, we want to calculate the sum over the microscopic degrees of freedom. Over here, we want to compute the sum of e to the h. So since we want to compute that average, then it behooves us to define a general average and see how to represent it. So ultimately, we want to evaluate the expectation of h, but over the unperturbed Hamiltonian corresponding to h naught, so something like this. So let's have a look. Let's define this more closely. So let's suppose I have some operator, let's call it A, that is a function of our microscopic spins, and I want to compute that with respect to our unperturbed Hamiltonian. So what do I mean when I write down those angle brackets? So what I mean is I say, I'm going to take my quantity A. It depends on the microscopic spins, but the microscopic spins I can write in terms of the block spins and then the sigma spins, the microscopic spins. So I can write them like that. And then I'm going to multiply by e to the h naught, which will depend on the block spins and the microscopic spins. And then I'm going to take an average over my small spins, my microscopic spins, and then I'm going to normalize it by the partition function of that one block. So I'm going to normalize it by e to the h naught of si of Si and sigma I. So that's what I mean by an average with the subscript 0. Okay, so that's how we do integration. How we do integration. So now let's try to do that. Now, for us, the thing that we want to compute is the expectation of the Hamiltonian, e to the Hamiltonian, and the Hamiltonian is h naught plus v. So actually, what we want to compute this e to the h prime, just depending on the block spin variables, is then going to be the sum over the microscopic variables of e to the h naught as a function of Si and sigma I. And then I've got V, which is the interaction between spins. And so I'm going to compute that with respect to the partition function, with respect to the unperturbed Hamiltonian. So that's the quantity that we want to compute. And what we're going to see is that this quantity, expectation of e to the v, the perturbation, that we will then expand in what's called the cumulant expansion. So I'll get to that in just a second. So that's the basic idea. So let's have a look at this. If we have m blocks in the system, one thing I want to make crystal clear. In writing this here like so, I mean this to be a multiplication. Okay, I want to make sure that you understand that. Okay, that's a multiplication. Why? Because I've got on the left-hand side, look over here, in the denominator, I have this normalizing factor here. So when I want to compute the expectation value of e to the h naught, then the partition function is actually not the expectation value of it, but just the trace over the microscopic degrees of freedom. So I have to multiply by the normalization factor. So that's why that factor is there. So this sigma here is because if I want to compute this object, just this thing over here, that thing is equal to the expectation value times the sum over the sigmas of e to the h naught. Okay. So I just want to make sure that that's clear. Okay. So if I have m blocks in the system, remember that all I'm doing there is computing the sum over the blocks of e to the h naught. H naught has no degrees of freedom other than the things inside each block. So then what that means is that when I compute the sum over all the microscopic degrees of freedom of e to the h naught Si sigma I, then that thing is equal to the partition function of one block and then raised to the nth power. Because the blocks are not connected, so they're independent. And this value here, this partition function of one block also depends on the value Si. Because Si is over here on the left-hand side. And so this thing will depend on Si. And so this thing over here, I can think of this as basically the partition function of m non-interacting blocks. Okay, so that's something that's easy to calculate. We've just got 3 spins and we have to compute their partition function. So let's go ahead and do that. So to calculate Z0, so we can just literally write it out. So Z0 depends on the coupling constant K. Remember, H has been set equal to 0. So this is the sum over the block spin values, S1, S2, S3 equal plus or minus 1. And then what is the Hamiltonian? Well, it's e to the k times S1, 2 plus S2, 3, whoops, plus S3, S1, all within that same block SI. Okay, and I have to do this for particular values of the block spin variables. So when I do this calculation over here, the one I've just outlined, here the states that I'm going to be summing over are S1 is equal to minus 1, S2 is equal to plus 1, S3 is equal to plus 1. That's one of the states when the total spin is equal to plus 1, and then the other one would be S1 is equal to plus 1, S2 is equal to minus 1, S3 is equal to minus 1. So I literally just sum over all these different possible states. I'm going to write them out for you in a minute. So let's see that more clearly. So to be more precise, so let's suppose we take SI is plus 1. So then what are the possible states of the system? We know that there are 4 different spin configurations. So the SIs, and then 1, 2, and 3, they can be like this. We enumerated them on a previous page. That would be this, and then this, and then this, and then this. So those are all the microscopic configurations that I have to sum over. So that then tells me that Z0 as a function of K is equal to, well, I've got 3 terms where the spins are, well, I've got 2 spins up and 1 spin down. So in these ones here, all of those terms, let me write it like this, those terms give me e to the minus k each, right? Because substitute those into here. So I've got S1 is minus, S2 is plus, S1, S2 times minus 1 times plus 1 is minus 1. And then I've got 1 times 1 plus 1 times 1. So then I've got actually 3 factors of e to the minus k. So I have 3 times e to the minus k. And then this last term, and they're all pointing in the same direction, that gives me e to the 3k. Because if all the spins are plus 1, then I've got 1 times 1 plus 1 times 1 plus 1 times 1. So that's e to the 3k in the exponential factor. So that is the value of the partition function for the block when s is equal to plus 1. Okay. Did everybody follow that? Before I go on, anybody got any question about that? Literally just put these values in to this sum over here on the left-hand side and then calculate it. So if we did SI is minus 1, so let's now do that. So I'm going to leave you to check this. What you get is you can enumerate what this vector looks like. So now they're minus 1, so it's now 1 up and 2 down, those are the four states of the system. And if I do that, then what I'm going to get is Z naught of K is equal to 3 e to the minus K plus e to the 3K. So the same thing as I had before. Actually, let me just check that that's correct. Okay. All right. So that's the result. And so now I can write that e to the Hamiltonian, the effective Hamiltonian for the block spins is equal to Z naught of K to the nth power times the expectation value of e to the v with respect to our unperturbed Hamiltonian. Okay, so far we did all the easy parts of the problem, and now we're going to have to compute expectation of e to the v. So this is what I'm going to do next is described in 9.6.3 of my book. This is on the perturbation theory. For the renormalization group recursion. So here's the basic trick. We're going to not do perturbation theory, we're going to do the cumulant expansion. So let me show you what we mean by a cumulant expansion. So the thing we have to compute is e to the v. And what we're going to do is a trick that sums this expectation value to higher order than would normally be the case if we just expanded e to the v as a power series in v. So let's write it down as a power series in v. So this is equal, this is equal to 1 plus v squared over 2 factorial plus higher order terms. And you can say, well, okay, so then this is just equal to 1. The expected value of 1 is 1, and then the expected value of v, and then the expected value of v squared times half plus higher order terms. So that would be what you would normally do as perturbation theory. But here's the trick. We know that the thing we want to actually calculate is the expectation value of e to the something. So what is the basic idea? So the basic idea is that if I want e to the v, I want to write that as e to the something. And I want to do it like this, not just some expectation of v plus something or other like that. So normal because we know that in the end, we're going to read off that it's e to the something or other. So why don't we already get it ready into that form? And it turns out that if you do it this way, this is called a cumulant expansion, this amounts to summing the series to a much higher level of accuracy than if you just did perturbation theory. And you're going to see this right now. So how do we see this? So the basic idea is to say, okay, fine, if that's what we want, then actually what we really care about is not the expectation value of e to the v, but the logarithm of the expectation value of e to the v. So let's just remind ourselves. Remember that if I have the logarithm of 1 plus x, so what is that equal to? You learned this on your mother's knee. It's x minus x squared over 2 plus higher orders. Okay, so that's the logarithm of 1 plus x. So what that means is then, if I want to compute the logarithm of the expectation value of e to the v, like so, then our x value is this thing on the left-hand side here. So this thing over here, that's what's going into our x on the previous page. So I can then write the logarithm of this as 1 plus x. So the logarithm of that is x. So that's going to be expectation value of v plus the expectation value of v squared times a half. So that's this first term. But then I also have this term over here. And this term over here then is going to give me an extra term, which is going to be minus 1/2 the expectation of v naught squared. So this term is coming from here. Now, why do I have v squared? Well, because in my x, I have this term, which is order v. If I use this v squared term, this one over here on the left-hand side, when I square that, that will give me a term of order v to the 4th. And I'm only working to order v squared. So all my corrections are all higher order in v, so I'll write them as order v cubed. So that means that consistently to this order, what I have then is that so with my x value being v naught plus 1/2 v squared, like so, then these are the only contributions at order v squared are the logarithm of e to the v is equal to 1/2 expectation value of v squared minus expectation of v squared, like so. That's the order, the square term, and then the first term is just expectation value of v0. So that's the order, and then there's the higher order terms. So can you see how we've mixed up orders in perturbation theory by doing this cumulative expansion? Now, we did it just by doing it by eye, but if I wanted to do it to arbitrary order, you can do that. You can write it out as a generating function. And what you can show is that if you had done this by perturbation theory, summed up all the terms, some of the terms could sum up as like a geometric series, and then would come into the exponential like this. So it's a trick for resumming a perturbation theory and making it more accurate. So in the end, then we can say that, actually, let me change color. So in the end, what we have then is that the expectation value of e to the v is then equal to e to the expectation value of v plus 1/2 the expectation value of v squared minus v squared. Bless you. Like so. And that's called the cumulative expansion. So it's particularly useful here because the thing we want on the left-hand side, we're going to call e to the h. So after we e to the h prime, the effective Hamiltonian. So after we've computed this, then we can simply read off what the effective Hamiltonian is. So the great thing about this is great because now we can read off that the effective Hamiltonian is just m log z naught of k. That comes from this factor in the front here of z naught to the m. So we can read that off, and then finally we have the term plus expectation of V plus 1/2 the expectation value of V squared minus V squared naught plus higher order terms. Okay, so so now we need to compute some of these expectation values. Okay. Oh, let me just say one thing. Where did this term come from? So this term came from writing that Z naught to the M is equal to E to the M log of Z naught. Okay. All right. Any questions about this before I go on to the next calculation? No. No, because it literally is. H prime is in the exponential. Okay. So now we've got this. So now let's go and compute all of these terms. Okay, so let's get started with the first term. So we're going to evaluate the expectation value of V with respect to the unperturbed Hamiltonian. So what we're going to do is I'm going to write, so V couples nearest neighbor blocks. So what we're going to do is I'm going to write that V is equal to the sum I not equal to j. These are nearest neighbor blocks, V, I, j, like so. And let's go and write out what that actually is. So we can see that because we know that Vij, just from our picture over here. So here's Vij. So Vij couples spin 3 on block J with spins 1 and 2 on block I. Okay, so since that's the case, then I can write that Vij is equal to K times the spin S3 multiplied by S1I plus S2I. So now I've got the two different blocks coupled like that. And so if I want to compute then V by J averaged with respect to our unperturbed Hamiltonian, so that's going to be equal to, each of those terms, S1 and S2, are going to give you the same amount. So it's going to be 2K, and then the expectation value of S3J, S1I, all evaluated with respect to the unperturbed Hamiltonian, which just couples spins within each block. Okay. Now, you may say, well, this is ridiculous, because in fact, we know that H naught does not couple blocks. So that means that I can write S3J, S1I. I can write that as equal to the product of S3I with respect to Hamiltonian 0 times S1 with respect to Hamiltonian 0, and that's in block I, and this one is in block J. Okay, so now let's go ahead and do that. So if I were to compute S3J with respect to my unperturbed Hamiltonian, let's write out what that is. So that's 1 over the partition function of a block, which I've called Z naught, and then it's the sum over the spins in block J, and then S3J, that's the thing I'm trying to take the average of, and then times the Hamiltonian for the block, which is K And then it's S1j, S2j, plus S2j, S3j, plus S3j, S1j. All of those spins in the Hamiltonian in the Boltzmann factor all come from the same block because our unperturbed Hamiltonian just looks at spins within each block. And we're only going to include in the sum here, in this sum over here, we're only going to include configurations which are consistent with the value of Sj. So you tell me what is the value of Sj. It can be either +1 or it can be -1. Take your choice, sum over all the configurations that give you that, and then we can compute this. So when we want to do that, then what we're going to do is we're going to say, well, Sj can either be +1 or -1. So let's take the case where Sj is equal to +1. So when Sj is equal to +1, then I claim that there are these are the terms that you have. So first of all, what do we have in the denominator? Well, the denominator is the thing that we calculated over here. So there's our denominator. So that we know is in the denominator. So that's e to the 3k plus 3e to the minus k. And that doesn't depend on what is the value of Sj. Okay. Now, when Sj is equal to, now I have to go through all of the configurations consistent with Sj is +1. So S1 can be 1, S2 can be 1, S3 can be -1, so on and so forth. Okay. So I claim that if you sum through all of those, what you get at the top here is e to the 3k plus e to the minus k. All I've literally done is put in the allowed values of Sj and put them into the sum, and that's what I get. So I'd like you all to check that. Okay. So literally is like 2 lines of algebra, but I want you to check that to make sure that you can reproduce that. Okay. So that's the result when Sj is +1. Now, what happens when Sj is equal to -1? So you do the same thing, and what you find when Sj is equal to -1 is you get minus e to the 3k plus e to the minus k over e to the 3k plus 3 e to the minus k. And again, I'd like you to check that, okay? It won't take you very long, but I don't want to ask you to do it right now in the lecture because I want to get to the next point in the calculation. Okay. So if you look at that, what's on the left-hand side, you can see, well, actually, what I've learned is that S3j is actually plus or minus times this function, depending on whether Sj is plus or minus 1. So I can write this as Sj times e to the minus k plus e to the 3k over e to the 3k plus 3 e to the minus k. Okay, so I've got the Sj out there in front. When Sj is +1, I get plus times that thing. When Sj is -1, I get minus that. So I can say that if you tell me the value of Sj, I can tell you what the value of S3j is. And now that's the same thing for SSI. So when I want to compute Si, so I'm computing now this term over here. This term is the same as before, except wherever I had j, now I have I. So this thing, we can say straight away, is going to be Si times this same function. e to the minus k plus e to the 3k divided by e to the 3k plus 3 e to the minus k. So now I can put it all together. So then the expectation value of v is actually equal to 2. Let's go back and through it. So I'm going to go up to here. So it's 2k times the product of those functions. So it's going to be a function I'm going to call phi of k, which I'm going to define in a minute. And it's this function squared. And then multiplied by the sum over I and j, nearest neighbor blocks, si, sj. And this function phi of k is e to the 3k plus e to the minus k over e to the 3k plus 3 e to the minus k. So to this order, let's just look at what the effective Hamiltonian is. Our effective Hamiltonian now to this order in terms of the block spins variables si is equal to some constant, which is just m log z naught of k, which is just some number. And then I've now got a new coupling constant k prime times the sum over nearest neighbors of the blocks si, sj. And then there's all the terms I haven't yet calculated, the higher order terms, the v squared terms. Okay. Any questions about this equation before I go on any further? Okay, no questions. So you can see that I've done two things. I've literally done the renormalization group transformation, and to this order in perturbation theory, and only to this order in perturbation theory, it turns out it does have the nearest neighbor form that my original Hamiltonian had. And so this is the nearest neighbor form to this order. And the new coupling constant, after I've done the renormalization group transformation, I can read off is 2k times phi of k squared. And as promised, the renormalization group recursion relation is some very complicated nonlinear function of the original coupling constant. But we've calculated it, okay? And now that we've calculated it, we can then use that calculation. So let's go ahead now that we've done all that effort to do the calculation, everything else we want to do is just applying the formalism. So the next thing we're going to do is, now that I've got the recursion relation, then I need to compute the fixed points and critical exponents. So let's do that. So fixed points, so I have k star is equal to 2k star phi of k star squared. That's the fixed point renormalization group equation. And so that implies that either k star is equal to 0 or k star is equal to infinity. Both of those are going to be sinks, as we've seen before. And then the other thing I can have is that 1 is equal to 2 phi of k star squared, and that means that phi of k star has the value 1 over the square root of 2, where this function phi is this ratio of these all those exponentials. So if I then compute what that means, I can invert this. If I invert this, I'm going to do a trick. I'm going to use define x to be the variable e to the 4k, and then I can say that phi of k star is equal to 1 over root 2. That implies that the corresponding k value is equal to 1/4 times the logarithm of 1 plus 2 root 2. Okay, you can check that. and that is a number that's about 0.34, something like that. Okay, so that is the critical K value. And remember what K is. K is equal to J over KBT. And so that tells me what is the critical temperature of the 2D Ising model. And so what we got was 0.34. And if you take Onsager, what he found was it's 1/4 log 3, and so that's about 0.27. So that's pretty good. That's not bad. Okay. And similarly, if I want to compute the eigenvalues, well, how do I compute the eigenvalues? Well, the thermal eigenvalue lambda t is equal to dk prime by dk evaluated at the critical point at k star. So I've got this, I know what k prime as a function of k is, because I've just calculated it over here on the left-hand side. So I go ahead and do that derivative and plug in the value I get for k star, and that gives me something like 1.62, something like that. And if I compare that with Onsager, that gave me, Onsager said that lambda t was equal to the square root of 3. Remember, we had that earlier on, and so that would be 1.73. So actually, it's reasonable agreement. And that's just working to order V. Okay. And we didn't have to do much work. Okay. Compared to solving the Ising model exactly as Onsager did, which is an amazing piece of work. So the next thing we can do then is we can say, well, can we improve this? And the answer is yes. We have to work to order V squared. So I'm not going to try to squeeze that in right now. We will start off next lecture showing you how to do that. It's just the same calculation basically, and I'm not even going to do all of it. I'm just going to show you how we construct it, and then you're going to see that we generate not just nearest neighbor, but next nearest neighbor interactions in the effective Hamiltonian. Okay, so I think we're going to stop there for today. So you've got a little bit of homework to do, which is to check this very simple calculation over here on the left side of the page. Okay, so I'm going to turn off Zoom, and then I'll be happy to take any quick questions.